This podcast is brought to you by LMU Munich.
The last lecture today, one short announcement. There was a ring found in the room. So if someone misses the ring, please see me after this lecture, okay? And now we start with Martin's second lecture on higher spin gravity.
Yeah, so thank you very much. So let's first recap what we did last time. So in the first part last time, I tried to convince you that higher spin theories are really interesting, and in particular higher spin gravity theories, like non-interacting theories. And I explained to you that it would be interesting to explore the connection to string theory a bit more, and in particular we are convinced that there is a connection, and it might also solve some problems, or we could find new quantum gravity aspects of string theory by just looking at higher spin gravity. And in the second part, then, we discussed a few examples, starting with spin 1, spin 2, and then going upwards. We discussed how we formulated three higher spin theories. The massive case, and later on also in the massless case, where we had an additional gauge transformation. And in particular, we saw that this Fronstal formulation of this massless higher spin theories, that they have some drawbacks due to constraints. But at the end, all the equations and also the Lagrangian existed and worked. So the question is now, can we generalize it? So how would we proceed? If you really want to make a theory interacting, say we have a scalar field and we have, say, an electromagnetic field and, or say in fermion an electromagnetic field, what we typically do is we replace the partial derivatives by covariant derivatives. And so does it also work for interacting higher spin theories? So the question is really about interactions now. And like we are trained, so what we always do is we just replace ordinary derivatives by covariant ones. And if we really do this for the higher spin theories, which we discussed, particularly for the massless but also for the massive case, then we encounter inconsistencies. So this does not work. It's even more complicated. You can think of, okay, so this kind of, this recipe, which is also referred to sometimes as minimal coupling, is just do the kind of minimal subset of basically recipes to couple two theories to each other. So this might not work. So can we do a bit more? So can we look at non-minimal couplings to get interacting higher spin theories? And it turns out that from the 60s to about the 80s, people argued that there should be no such higher spin gravity theories. So what they always do is then they write down no-go theorems. And here I consider just the massless case. So to be honest, I don't have too much time to discuss these theorems in detail, but if you really want to look at a nice review, then you can look at a paper by Porati from 2008, which nicely summarizes the situation. So here I will just mention like the three standard no-go theorems which we have. And what is always important if you discuss no-go theorems, you should always think in terms of how could I evade the conclusion. So what is basically the assumption we made, and is this assumption really true or not? So the first no-go theorem is by Weinberg from the middle of the 60s. And this approach is based on the so-called S-matrix approach. So he looked at S-matrix elements and in certain soft limit and realized that there are no consistent long-range interactions. By massless bosons with spin larger than 2. And of course, the important word here is long range. You can evade his no-go theorem by just assuming that these higher spin interactions, that they are short-ranged. And then the statement of Weinberg cannot be proved, so it cannot be proved for short-ranged interactions. Then there was a second attempt by Aragon and Besser in 1979. And their idea was not to look at a specific example, but to look at interactions with gravity. So how do these higher spin fields interact with gravity? Because the interaction with gravity is universal. And they took a certain limit, the soft limit. But however, their arguments were based on a Lagrangian formalism. And if we use a Lagrangian formalism, like if we restrict ourselves like to just first or second derivative terms in Lagrangian, then we make an implicit assumption about locality. And there's no reason why such a higher spin gravity should be local. So in other words, this no-go theorem could be evaded by just looking at non-local higher spin gravity theories. And so there was a third kind of no-go theorems by Weinberg and Witten, and also generalizations thereof. And this is like from the 1980s. And basically what they say is that no massless higher spin particles, so with spin larger than 2, can be consistently coupled to gravity in flat space. So they make it now clear that their no-go theorem is just valid in flat space-time. And you immediately have to ask yourself if really higher spin gravity is a limit of string theory. It has to exist. So how could we evade these no-go theorems? But because we can formulate string theory in flat space, and so we can also take the tensionless limit. For me, this kind of no-go theorem is not so important because of this word flat space. But nevertheless, for you, it's really crucial. You should think about it. What does string theory, or how does string theory help us so that we might be able to formulate the tensionless limit of string theory in flat space consistently? So what I will do in the lecture, I will focus on asymptotically anti-de Sitter spacetimes, because I'm interested in these generalizations of this ADS-CFT correspondence to like free field theories or to minimal conformal field theories, because, as I told you last time, both of these new dualities are tractable in the sense that we can perform explicitly calculations on both sides. And so I don't worry about this no-go theorem here. And it turns out we can really formulate consistently higher spin gravity in ADS, so an interacting theory. And this is due to Vasudev and collaborators. And that's basically one of the goals of the lecture, to really understand their system, what they've written down. But it's, if you know the equations, then you know it's a mess. They're very complicated, and so I really start with simple systems. So what I do is I look only at three-dimensional higher spin. This has the advantage that originally this Vasudev theory has infinitely many spins coupled to each other. And you cannot just truncate the theory to a finite number of spins, unless you are in 3 dimensions. And so this is what I will do. I will start first with a spin 2 gravity theory in 3 dimensions. Then I will add a spin 3 degree of freedom. Then I will show you how we can add up like spin 2, 3, 4 up to n. And then at the end we discuss the Vasudev theory. And so the plan of the remaining 3 lectures is the following, or 2 3/4 lectures. First, in chapter 3, so this was chapter 2, it was about free fields. What I will study is 3D spin 2 gravity. With negative cosmological constant. And in particular, I will show to you how we can compute the so-called asymptotic symmetry algebra of that theory. And I will also show to you how we can reformulate the Einstein-Hilbert term and the negative cosmological constant in terms of what's known as a Chern-Simons theory. And so today I will only talk about this part. It seems to be a bit boring, but in particular the reformulation in terms of Chern-Simons fields will help us immediately to generalize it to consistently interacting higher spin gravity theories. And that's basically what I will do in chapter 4. So 3D higher spin theories involving, in the simplest case, spin 2 and 3, or in the next to simplest case, spin 2 to 3 up to spin n, where n is some finite number.
Can you just have spin 2 and spin n, spin 4, or you have to have the whole?
We come to that point. Yes, you can have spin 2 and spin 4, but other combinations might be a bit more tricky. And we will discover something which people discussed in the 90s, W algebras. Yes, the first row is smiling. People reacted the first time when they saw these papers, okay, they thought, okay, why does this appear again? Okay, good. So then chapter 5 is about the Vasudev theory. So then we really go into the details and couple in infinitely many spins, and also, say, a scalar field. And at the end, if time permits, I don't know, let's see, we discuss black holes in higher spin theory. And we also discuss something like what is the space-time notion in these higher spin theories. And in order to discuss this, so there's no final answer to it, but in order to discuss it, we look at a quantity which might capture it, and this is entanglement entropy. Okay, but let's see if we can also come to that point. Good, so let's start now with point 3. Yes?
Of the Arnold Noodle Theorem, where does massless field enter?
I think this is how they write down their Lagrangian formalism. We can discuss it later in detail, but I think they made also in this Lagrangian formalism, they made their implicit assumption that it has to be massless. Okay, so chapter 3. So the theory which we are interested in has the following action. It's just an Einstein-Hilbert term. So the p factor is just 1 divided by 16 pi times the Newton constant, which I call G3. I integrate over manifold M, Lorentzian manifold, say, d3x squared of G. And then I've got here the usual Ricci scalar and 2 divided by L squared. So this term here, 2 divided by L squared, is the minus 2 times the cosmological constant. And so you see that in this case here, the cosmological constant is minus 1 divided by L squared, and it's negative. And so L is basically the characteristic radius of curvature, in particular of the vacuum solution to this equation, which is just ADS3. And so L is just the radius of curvature of ADS3. And one of the solutions of the system, which you all know, is like ADS3 in global coordinates. Which for example, can be written in this form. So this ds squared is just minus 1 divided by r squared divided by l squared times an dt squared plus an dr squared divided by 1 plus r squared divided by l squared plus an r squared d phi squared. And r is the radial direction in ADS space. So if r goes to infinity, we reach the conformal boundary of ADS3. And t and phi are just the coordinates of this conformal boundary. So basically here r runs from 0 to infinity, and t is the real number, and phi basically parameterizes a circle, so it runs from 0 to 2 pi. And so here, these are the basically coordinates of the conformal boundary, and together, so this is the time direction, say, and so this is the phi direction, so together what they form is a cylinder. So this is t, and this is phi. Okay? Good. For what we will do in the following, in particular if we want to use the ADS-CFT correspondence, such a coordinate system is not so convenient, in particular if you want to read off, say, the energy momentum tensor. So what we usually do there is we go to the so-called Pfefferman-Graham form of the coordinate system. And this just says that basically this factor here should be written as a d rho squared, and all the boundary coordinates should be orthogonal to this direction. So basically, you just have to find now the coordinate transformation so that this factor here could be written as d rho squared. And this is what I leave for you as an exercise. It's not very difficult. It's really not very difficult. So if you really go to the so-called Pfefferman-Graham form, so then you find a coordinate system so that this ds squared here could be written as an d rho squared plus a metric gij in the transverse coordinates dxi dxj. So x0, say, is the time, and x1 is just phi in our case. Okay, here for later convenience, I introduce a t divided by L, and x1 is just the phi. So the reason why I introduce here an L is because t is dimension full and the phi is usually dimensionless. So just to treat it on the same footing. And so this Pfefferman-Graham form tells us that this gij is a function of x, so of t and phi, but also of rho. So the Pfefferman-Graham form just tells us that there are no mixed terms, no d rho dx or d rho dt or d rho d phi. And it tells us even more. It tells us how this gij of x and rho looks like near the conformal boundary. The conformal boundary is at rho going to infinity. So what I can do now is I can expand this metric gij. So gij of x and rho for sufficiently large rho could be then written as e to the 2 rho divided by L gij0 of x. So this depends on x and rho. So this is what I already split off the vector, the row dependence. So I've got a Gij 0 of x plus, and then I've got also subleading terms, which are then constant in row, for example. This is what I call this Gij 2 of x, plus terms which go like e to the minus 2 rho divided by L, for example. So these terms here. But this is only true, so this expansion is only true generically for rho going to infinity. So why do I tell you this? It's important later on for a point which I want to make. And it's also important in particular for the applications of ADS-CFT. Because ADS-CFT tells us if we expanded this Gij of x and rho, we can read off from that expansion two quantities. We can read off this coefficient Gij 0 of x. And this is just the metric at your conformal boundary. So basically the metric where your conformal field theory lives. And so usually what we take here is we just take a flat metric. So we take this cylinder coordinates here. So it's, in our case, this Gij 0 of x is something like minus dt squared plus d phi squared. And also probably some L factors, which I ignored. Okay, what about this quantity here, Gij 2 of x? This quantity, and this will be important if we study later on the asymptotic symmetry algebra, this quantity is related to the energy momentum tensor of our conformal field theory. So it's related to, it's not equal. Okay, and so this is the only thing which I really will need later on from ADS-CFT. Are there questions regarding that point? Yes?
Does the Pfefferman variant still working in the digital case?
I'm sorry?
Pfefferman variant form is still working in the digital space case?
In anti-de Sitter space, you see? You mean?
I mean, digital case.
There are some subtle issues, so you have to be a bit careful, but in principle it should work. Okay, good. So what we will do now is we take Gij 0 to be just this cylinder, which I already advertised. So basically, Gij 0 times dxi dxj, and you can immediately read off this from this metric if you take r going to infinity. So if r goes to infinity, what we can do is we can drop the 1 here, because 1 plus infinity squared is always infinity squared. And we can also drop here this 1, because this one is larger than this one. So what we see is, and of course we can ignore the dr squared term. So what we see is that the boundary metric then is dt squared divided by L squared plus nt phi squared. And so this is precisely what I call dx0, it's a minus dx0 squared plus dx1 squared. And what I will do now, whenever you see such a metric, I will now introduce light cone coordinates, just to write this as dx plus times dx minus, and I will choose a little bit unconventional sign. Namely, I will choose x plus to be phi minus t divided by L. So in other words, this is just x1 minus x0. And x minus to be phi plus t divided by L, which is x1 plus x0. So here the sign might be a bit strange, but later on I will explain to you why I have chosen this sign convention. And so then we immediately see that g plus minus 0 and g minus plus 0 is just 1/2. Okay, so what we usually do is we don't work in Lorentzian signature, as here, but we work in in Euclidean signature. So what we do is usually we do a Wick rotation, and that explains this sign convention here. So we replace our time t by tau, which is just I times t. And if I put this back in here, then I see that x plus is now phi plus I tau divided by L. And this is what I will call W. And x minus to be phi minus I tau divided by L, which is just a complex conjugate. Okay, and so this explains, I wanted to identify x plus with W and x minus with W bar. And so this explains this sign convention here. Good. So let's now write down the most general solution which we can think of for this gravity theory. And usually if you do this like in 4 dimensions, 5 dimensions, whatever, this is a very, very complicated task to do. Yeah? Just ask the people doing numerical GR or general relativity in general, then they will tell you, okay, it's very difficult to write down the most general solution. But here we are in 3 dimensions. In 3 dimensions, all the spacetimes, the solutions, are locally flat. And I will explain to you later on in the so-called Chern-Simons formulation why it's referred to as locally flat. And so it turns out that this following 3-dimensional metric, which we will see from now on many times, namely this one here. So ds squared is just 4 times G3 times L. L of omega, the omega squared, plus L bar of omega bar, the omega bar squared, plus an L squared e to the 2 rho divided by L, plus 4 times the 3-dimensional Newton constant squared, L of omega, L bar of omega, e to the minus 2 rho divided by L, d omega bar, plus an L squared, d rho squared, is for this kind of gravity system an exact solution. In particular, it doesn't matter precisely what L and L bar are. They can be arbitrary functions of W and W bar. The only important point is that L should only depend on W and L bar should only depend on W bar. Otherwise, they are not constrained. In particular, and I'm sorry for this notation here, L bar does not mean that it's the complex conjugate of L. It's another function. You can choose whatever you want. So this is an exact solution for any choice of L and L bar. It's not even just an exact solution, it's the most general solutions, up to, of course, some trivial diffeomorphisms. We can always do diffeomorphisms, which is asymptotically anti-de Sitter with this flat boundary matrix, and of course only in this system where we don't have any matter degrees of freedom. So the question arises now, what is this L of W and L bar of W? And that's why I mentioned this beforehand. So you already realized that this metric here, up to a factor of L squared here, but this doesn't matter. So here I didn't include an L squared, is already in this Pfefferman-Graham form. So we can now determine what this Gij of x and rho is. The Gij of x and rho are just the first two lines, already contracted with dxi dxj. Okay, so what we have to do now is we just have to basically figure out this limit here for rho going to infinity. Then we can read off Gij is 0 of x. And we, of course, get our cylinder. And then we can also extract the Gij2 of x. And in particular, there are two components which are multiplied by a constant with respect to rho. And this is this one here and this one here. So basically, GWW is up to this prefactor here, just G2WW is just L of omega, L of W, and GW bar W bar is just L bar of W bar. So these are the two unknown functions which we can choose. But I told you that this coefficient is related to the energy momentum tensor. And in this case, the relation is that you just have to divide out by this factor in front. In other words, L of W is just T, the energy momentum tensor, in the direction WW, while L bar of W bar is just T of W bar W bar. This tells you ADS CFT. This is also what I've already written down here. So if you don't believe this here, then you don't believe what I'm writing down now. But otherwise, just accept it. And of course, the energy momentum tensor is traceless, though there is no T of WW bar term. Good. So now let's discuss some of these three-dimensional metrics. Let's discuss some examples. Sorry, it's now a bit inconvenient, but okay. So here, this is the metric, and what we can do is we can choose any function you'd like. So the first one is, let's put both of them to be 0. So let's say L of W and L bar of W bar should be 0. Okay, so if it's 0, then this term drops out, this term drops out, this term drops out, okay? So it's the only thing which survives is basically an L squared d rho squared plus an L squared e to the 2 rho divided by L dw bar. And you now can rewrite this if you don't immediately recognize this. So this is just ADS3 in the Poincaré patch. Okay, so this is very simple. So the other thing which we can do is we can set both of the ones to a specific constant, which is just L divided by 16 G3. So here we have got an 4G3 times L in front. So if we set L of omega to be minus L divided by 16G3, then what we've left with is minus L squared divided by 4. And here also. And so what you then realize is, if you really write down this metric, and if you think about it, so this is just ADS3, but in the so-called global patch, or in global coordinates. Yeah. So a simple exercise now is just do it, and then you should be able to link it to this kind of coordinate patch, because this is also the global ADS. And what I can also do, and this will be important later on for the higher spin black holes, I can set L of W to be this constant parameter. So far all these parameters are constant, not dependent on W or W bar, or this one here. So we have got two parameters entering, namely M and J. And so this is the celebrated BTC black hole, probably in an unfamiliar coordinate system. And M is the mass, and J is the angular momentum. Okay. Good. So these are specific examples for this three-dimensional metric. Yes. It's not really visible in these coordinates, but you can transform it in such a way so that you see the horizon. You can ask the same question, by the way, when we discuss higher spin black holes, because that's not so obvious. Okay, good. So another thing which we can do with this three-dimensional metric is, from this three-dimensional metric, by some manipulations or by some arguments, we can now calculate the so-called asymptotic symmetry algebra. And this is a bit of a technical part now. So if you want to feel asleep, now it's a good point. I wake you up later on and just tell you the result. So I want to argue now that there exists a coordinate transformation of the following form. So basically, my coordinates W, W bar, and rho are mapped to coordinates which I call just with some prime, such that we start from this metric and we end up with the same metric, with the same form of the metric. However, what we changed is basically this L of W and this L bar of W. And it's really simple to write down this diffeomorphism. What I will do is I will basically give you the diffeomorphism in an infinitesimal form, and you can check it on your own that really this form basically stays the same. So this is just it's a straightforward exercise. I tell you what you have to do, but it's not something which you should do on a blackboard. And for this whole metric, it's a bit complicated. So I will restrict to a simpler case, which, however, turns out to be not spoiling the argument. So later on we can extend the argument in a straightforward manner. So what I will do is I will take L bar of omega bar to 0. And then you, of course, immediately see that this metric simplifies a lot. And then we use the following infinitesimal diffeomorphism. Namely, my rho bar is given by rho plus 1/2 times a function epsilon of omega, and I take the derivative with respect to omega. Omega prime, so this coordinate, is then given by omega plus a small correction, which I take to be epsilon of omega. And omega bar prime is just given as omega bar plus 1/2 e to minus 2 rho. And then I take here the second derivative of this epsilon of omega. So basically this epsilon of omega controls my diffeomorphism. And now I have to be honest, I did this exercise twice. And in the last moment I changed here the signs. Unfortunately, when I did it once, like a few days ago, I thought the other signs are the correct ones. But yeah, you will find it out if you do this exercise. Okay, so this is the coordinate transformation, and the claim is that this three-dimensional metric, the form is the same. However, L and L is changed. L of W is changed. So of this 3D metric which I wrote down is the same, but in this primed coordinates we have an L prime of omega, and here I don't write down of W. I don't write down an W prime. I want to evaluate it at W, and this is given by the original one function plus a small correction. And this small correction, okay, let's put here an epsilon. This small correction is given in the following form. It's an epsilon, of course, of omega times the derivative of L plus 2 times, okay, once I should, I guess, specify all the arguments. It's always W as argument. And then we have got also a term which depends on our Newton coupling constant. It's a minus L divided by 8 times G3, and there's a third derivative with respect to epsilon. So this is the result. Have you seen this transformation law beforehand? Let me remind you, this L of W, probably I should have stated here, is the T of WW. And this is precisely the transformation law of the energy momentum tensor for a C of T. And then we can read off from here what the central charge is. And this is also clear right from the beginning, because let's look at our diffeomorphism, which one we used. Let's put rho going to infinity, because we want to see how this diffeomorphism act on the conformal boundary. Okay, so rho going to infinity. And just look at the omega, sorry, always say omega, W prime and W bar prime. Then you see W bar prime stays the same, because if you take rho going to infinity, this exponential factor drops, but the W prime is just W minus epsilon of W. And this is, at least for W, it's basically half of a conformal transformation. And for a conformal transformation, you can transform your W and also your W bar with independent parameters, epsilon of W and epsilon bar of W bar. But that's the reason. So basically, what we've done, we've looked at a diffeomorphism which at the conformal boundary just reduces to a conformal transformation. And we looked at how this L, or our energy momentum tensor, at the boundary changes. Okay. And now from this, basically, you can immediately, because we can identify this L of W with T WW, we can read off the OPE for the energy momentum tensor. So the OPE for TC and TY is basically C divided by 2, 1 divided by C minus W to the power of 4, plus 2T of W divided by C minus W squared, plus okay, this is the usual OPE, and the only thing which we have to fix is the C here, and the C we can read off from this coefficient here. It's not precisely this coefficient, but it's one which differs by a factor of 6, and I explain to you now. So this C is then basically this times 6, so this is times 3L divided by 4 times G3, which is the 3-dimensional Newton constant. So this is the central charge. So what's the link from here to here, basically? What did I do? So a trick is basically to write down the Noodle Theorem, probably in a little bit unfamiliar way for you, if you've never seen it beforehand in such a way. So the question is, how does the energy momentum tensor, or this L, changes under such a conformal transformation? And what I'd have to take is I have to calculate the residue of the following. Okay, sorry. Let's write it down here, otherwise it's. So this delta epsilon T of omega is just the residue of the following expression. So it's an epsilon offset T of C times T of W. And I have to take the residue when C approaches W. Okay, so what I do now is I put in here this OPE, because the OPE just produces me the singular terms here. Let's just consider this term here. So, of course, we have to put in all 3 terms, but first focus on this one. So then we have, if we put it in here, we have an epsilon of C times dW T of V times divided by C minus W. And the question is, what is the residue of this term? we already have an 1 divided by c minus w structure. So the residue is just the coefficient in front, and of course we have to set c to w. So the coefficient in front is an epsilon of c times an dt by dw. And so if we take c to be w, then we reproduce this term here. Okay, let's do it for this term here. Here we have an 1 divided by c minus w squared, if we insert it here. And we have an 2t of w times an epsilon of c. So now you think that the residue is 0 because there's no 1 divided by c minus w term. But what you can do, of course, okay, you can write this term here as minus d by dc of 1 divided by c minus w. And then, okay, also here in this residues you can do a partial integration. And so basically your d by dc hits now your epsilon of c and your t of omega. And, okay, sorry, I wanted to write it in, I think I wanted to write it in this way, it's better. D by dw of 1 divided by c minus w, then I do a partial integration. So this d by dw then just hits this t of w term and not the epsilon of c. So it's 2 d by dw of t of w times epsilon of c, and then I take c going to w and I get this term here. And now it's just here what you have to do is you have to do this trick 3 times. So you get a 3 factorial, that's precisely the 6 difference, and then you can read off this c. Okay? Good. Too many words for a simple thing, but nevertheless. Okay. And so what you always can do is, what you also can do is, and this is also good exercise if you've never done this, because I think Matthias Gabeldiehl might present it a bit different way. So he will probably put it in terms of the Virasoro generators. So you can insert this t of c above here with this expression here and can work out the commutation relations for ln and lm for the Virasoro algebra. So okay, upshot of this calculation. We've set L bar of omega bar to 0. So this was our simplifying step. But then we saw we get 1 copy of a Virasoro algebra. Now we can do the same thing. We can set L to 0, but leave L bar unspecified and do a similar coordinate transformation. Then we get also a copy of the Virasoro algebra. And then we can combine both results. And what we get is, and this is really the asymptotic symmetry algebra of this 3-dimensional Virasoro algebra, of this 3-dimensional gravity theory, it's 2 copies of a Virasoro algebra. So the asymptotic, so this is the upshot basically of this calculation, is the asymptotic symmetry algebra of 3D gravity with ADS boundary conditions is Virasoro plus Virasoro. And this was known long before ADS-CFT, to be honest. This was done by Brown and Hainaut. And this could be viewed as a precursor of ADS-CFT. Okay, good. So this is 3-dimensional gravity as you might have seen it, except this asymptotic symmetry algebra and probably this exact solution. So what we can also do is we can reformulate this 3-dimensional gravity as a so-called Chern-Simons theory. And this is the next step which I want to present to you. Then in the Chern-Simons theory, what I will do is I will also show you how the solutions look like, basically how we get the metric back. And I will also discuss the asymptotic symmetry algebra, which of course has to be Virasoro plus Virasoro, otherwise we would have done a mistake. And while this kind of metric-like formalism here is very difficult to generalize for higher spin gravity theories, the Chern-Simons formulation is simple. It's very simple. You can even work it out on your own. I tell you at the end what you have to do. And then we can work it out until Thursday and skip the first lecture on Thursday if you want. Okay, so first remark that the vacuum solution of this three-dimensional gravity series, of course, ADS3, and the isometry group is just SO2,2. And we can write this SO2,2 as 2 copies of SL2R. Okay, first nice thing. By the way, this is related that we also have 2 copies of the Virasoro algebra, because the Virasoro algebra have Virasoro generators LM. And if you restrict your M to 0, 1, and -1, you discover an SL2 subgroup. And this is precisely this one here. So this is not a coincidence, it's some nice result. And those SL2R algebras here play an important role when we want to formulate this in Chern-Simons theory, because they are just the gauge group of the Chern-Simons theory. Okay? So what we do is we have to package now our data from the metric-like formulation to our Chern-Simons formulation. And so what's the data basically of our metric-like formulation? Of course, this is the metric, which you can reformulate in terms of an Vielbein. We have an Vielbein EA, which we can write as an EA in one form, strictly speaking, EA mu dx mu. So mu runs from 0, 1, 2, which basically labels the curved coordinates. And A also runs from 0, 1, 2, which labels the flat coordinates on the tangent space. And so what's the feature of this E mu A is, if you have the metric, you can think of this Vielbein as like the square root of the metric. In which sense? You can write this metric as a Vielbein squared, namely you can write it as E mu A times E mu B times eta AB. This eta depends now, if you want to work in Lorentzian signature, you have an eta. If you want to work in Euclidean signature, you have a delta here. So here I assume that we work in Lorentzian signature. Okay, so this is the first data. And the second one which we have is a spin connection. And a spin connection can be also expressed as a one form in curved space. So it's basically an omega AB, which has components omega AB mu dx mu. Okay? Good. So it has 2 indices, and this has 1 index, 1 flat index. So it doesn't make sense to group them together because they should have the same index structure. However, we are in 3 dimensions. And in 3 dimensions, we have an antisymmetric symbol, so the 3 indices. So what we can do is we can introduce here, probably call it dual spin connection. So with just 1 index, omega A, and this is just an epsilon ABC omega BC. And here, if I raise and lower the indices, so the flat ones, I have to raise and lower them with eta, and the curved ones, the mu and u, have to be raised and lowered by the metric. Okay, so now we have an object, this object here, and this object here. Both of them have just 1 index, have the same index structure. So let's group them together. So what I do is, I introduce now gauge fields. Again, A and A bar. A bar does not mean it's the complex continuum, it's an independent one. And the gauge field should be valued in SL2R, both of them. So basically I can say this A is just an AA times JA. Let me call me here JA tilde. I guess I can. Okay, JA, yes. And also the A bar. So JA are just the generators of SL2. And this A, probably I should have chosen a different index. So the AA is just a linear combination of E and W of the E and omega of the spin connection and the field bind of this form. And here also this characteristic length L enters. We can set it to 1 if you want, then it is gone. And A bar A is just an omega A plus 1 divided by L EA bar. EA, sorry. So the only difference is here the sign. Okay? And so for later convenience, if I really want to do calculations, I should give you my preferred basis for this J's. So basically, J0 I take to be 1/2 1 minus 1, 0, 0. J plus 1 I take to be 0 minus 1, 0, 0. And J minus 1 I take to be 0 plus 1, 0, 0. And all three satisfy these commutation relations. Jm, Jn is m minus n, Jm plus n. Okay? So this is my choice of basis. And what you should recognize is that if I calculate the trace of JA times JB, so trace of JA, JB is just 1 it's 1/2 eta AB. Okay. Good. So this is just so this A and A bars are the gauge fields. We have 2 copies of gauge fields, 2 independent ones. And what I also have to introduce is the so-called Chern-Simons form. Which I call GS of A or GS of A bar. And so this is just A wedge dA, so it's in 3 form, plus 2/3 A wedge A wedge A. And you would naively conclude that A wedge A or A wedge A wedge A, so this is 0 because of the antisymmetric property of the wedge product. However, please keep into mind that these A's are Lie algebra valued. So then this statement is no longer true. So this term is really non-zero. And then what you can write down, the simplest action you can think of is basically something like k divided by 4 pi, and I tell you later what k is. I integrate just this form here, take the trace beforehand, and I integrate it over my 3-dimensional manifold. I take the difference. Okay? And if you now go back, and this is a good exercise, and if you've successfully completed that exercise, I can give you Another exercise, which is even more complicated, but then you can write on paper, is basically plug in A and A bar. You will get it next time on Thursday. So, plug these two in it, calculate it, what happens, and what you get is, get your prefactor. I fixed this prefactor for you because I tell you later what k is. And so this one looks like d3x squared of absolute value of g r plus 2l squared, 2 divided by l squared. And then we have on boundary term omega I wedge EA. So there's a boundary term. Okay, so what you recover, this is precisely your Lagrangian for your three-dimensional gravity theory. And so this is also a boundary term. Of course, we know that also in gravity we also have to add boundary terms to make our variational principle well defined. So these are usually referred to as Gibbons-Hawking term. And this is precisely the Gibbons-Hawking terms. Unfortunately, not the entire term, but just 1/2 times the term. Okay? So basically, Einstein-Hilbert term plus the Gibbons-Hawking term, the action is not the same as this action here, as the Chern-Simons action. So the values, if you just plug it in, they disagree. However, the equations of motion are the same. Because for the equations of motion, we can drop the boundary terms. Okay, so the exercise was to show this identity. And so what it tells us, this identity, is that at a classical level, three-dimensional gravity is the same as Chern-Simons theory with gauge group SL2 plus SL2. And we have to fix this k, where this k is just, let me rephrase it in terms of the central charge is c divided by 6, or let me rephrase it in terms of L and T3. It's L divided by 4 times T3. Okay, good. So we see now that both theories are equivalent at a classical level, not at.
Why did you choose the minus sign? Why is it not more natural to add them?
Then you don't get the. Yeah, but we want to rewrite it. So in other words, basically the Chern-Simons, so the so-called Chern-Simons level, that's basically this k what I've written down, has to be opposite for the two gauge groups. Otherwise, you don't get the Einstein-Hilbert term. You get some other term.
So there's a k bar which is equal to minus k.
In principle, you can phrase it this way, yeah. And then you can ask, okay, what happens if they are not equal and so on. No, I said to you, okay, we don't argue that the quantized theories are the same. I think this is not true. The quantized theory might be different. But what I just wanted to argue is that the equations of motion are the same. And you can really do it. You can write down now the equations of motion for the Chern-Simons theory and put back in your E and your spin connection, and you see that you get the gravity equations. Yeah, so that's another simple exercise for you. So basically, write down the Chern-Simons equations of motion. And so the equations of motion are just that the field strength tensor, which is dA plus A wedge A. So if you vary this Chern-Simons term here, then you get dA plus A wedge A times the variation, and this therefore has to be 0. In other words, the gauge field has to be pure gauge, so that it's a solution of the 3D gravity, and this has to be the same. So this is the first thing which you encounter. And the second thing which you also encounter is that you have a gauge theory. So you have a gauge transformation. You can do gauge transformations. We have two copies of gauge fields. So we have two different, can do two different gauge transformations. So what we can do is we can take a gauge field A tilde, which depends on, say, W, W bar, and rho. Okay, and can transform it with a function or with an SL2 valued function. So this is group valued times, oh, I've written down here C, so that's. Let's call it, here I ignore the arguments. And we can do the same for A bar. Just for later convenience, I choose a different sign convention. So you can ask, why do you do this stupid thing here? B bar is not the complex conjugate again. And so it's okay. And you can also do it for infinitesimal transformations. And I need them later, so that's why I write them down. So you can say B is like e to the omega, and B bar is e to the omega bar, and just look at the two transformations to first order. And then what you get is that your delta A bar, which is just your A tilde, no, why do okay, let's start with delta A is an A tilde minus A, and so what this is, it's an A comma lambda plus D lambda. And of course you can also do it for the barred connection. Okay, good, so this is Chern-Simons theory. And now the question is, how do the examples which we studied in the metric-like formulation look like now in this Chern-Simons formulation? So what is Poincaré ADS? What's the global ADS? What's this three-dimensional metric which I've written down here? So the Poincaré ADS is very simple. It's the A is just an e to the rho times J1 C plus an J0 d rho. This is the A connection and the A. Okay, here from now on, sorry for this. So from now on I set L to 1 because I didn't want to bother with L factors. You can restore it if you just rescale rho if you want. And A bar is given as a J minus 1 dC bar minus J0 d rho. So these are the two gauge connections. And so how do we get back the metric? So for the metric, in order to get it back, what we need is we need the field bind. We need EA. So what we have to do is, and this is, you see from here, you have to take the difference of both, like E minus E bar. Then the spin connection drops out, and you are just left with the field bind, and then you have to multiply it by L half. So from this you get like the field bind EA, which is like L divided by half AA minus A bar A, where A basically calculates just J1 and J0 and J minus 1 and labels it. And then is the question, how do I get the metric? So the metric, again, ds squared was just my G mu nu dx mu dx nu, or no, sorry, I didn't want to write it this way. I wanted to write G mu nu. So G mu nu is just an E mu A E nu B times eta AB. So what's eta AB? What's the most complicated expression which we can use? And I said to you that my generators are normalized in such a way, and there's an eta AB in it. So I'm desperate, so I just plug this in. So this is traced JA, JB. And so then I can put in back here the E mu A and E mu B. So these are just functions. So I can put it inside the trace. And so this is nothing else than trace of E mu, E nu. So whenever you have two field lines, E, you calculate them this way. Then you express it as one form. So you get an E mu, square it, so I'll calculate E mu times E nu, take the trace, put a 2 in front, you get the metric. And if you really do it for this case, then you get the Poincaré metric for ADS. Good. So the ADS in global coordinates. So, which I call, because I need it later, AADS. So this is given in this form. It's an e to the rho times G1, and this will be really the starting point later on for computing higher spin black holes. So that's why I write it down so that you are familiar with it. So it's in J0 d rho. And then the same with A bar. And if you now use my preferred J matrices, then you can really show that you indeed get global ADS. Okay, so this is the two connections. And at the end, what I really want to discuss now is basically what do we call asymptotically ADS in this Chern-Simons framework. Of course, what we want to have is that asymptotically we get this connection here. So this means that we cannot change anything here and at this coefficient here, because if you take then rho going to infinity, then the connection which we compare with this connection would have a different coefficient here. However, here we could basically change this. We could, instead of 1/4, we could just write another constant. It would be still ADS, because if you go rho going to infinity, this term drops out, so this is not important. So, and this motivates the following definition, what asymptotically ADS boundary condition is. So this is basically, if you compare your A, your gauge connection which you have, for example, for a black hole, with this ADS connection here, so you compute the difference, and then you go to the boundary. So this means you send rho going to infinity. So then, these two things should only disagree in order 1 terms or in terms, so in constant pieces, or in terms which go like e to the minus rho, e to the minus 2 rho, and so on. And the second condition which we have is, you see here this AADS only has a DC in it. It has no DC bar in it. So this means that we also force that A of C bar should be 0. And the same also holds for A bar. So we say that A bar minus A bar ADS at the boundary is of order 1. And you see here that A bar ADS only has a C bar in it, DC bar. So we say that A of C should be 0. Okay, so we know now what are the asymptotic boundary conditions. Okay, so what I haven't done, so what I will do in the beginning of the next time, I didn't write down the gauge connection for this three-dimensional metric. And we also should discuss how the asymptotic symmetry algebra will emerge in this Chern-Simons formulation. But I think this is enough for now. And yeah, are there any questions?
These components which are 0 are these ADS algebra components?
So this one here?
Yes, is the ADS component?
In principle, it's the ADS. So like, okay, so this boundary condition means I have got a gauge field. And I want to compare it to this gauge connection here. Of course, ADS in the C bar direction is 0 automatically, so because I've written it down here. But also, the gauge connection, which I give you, also this C bar component has to be 0. If it's non-zero, then it's not a boundary, then it's not asymptotic ADS. Okay? However, this does not mean that the Vielbein in the C direction has to vanish, because for the Vielbein we have to take a difference between A and A bar. A, of course, in the C bar direction is 0, but A bar in the C bar direction can be non-zero, has to satisfy this here. Okay, so this does not mean that the Vielbein in the C bar direction is 0. Further questions?
To which extent it's true that on-shell solutions are your gauge? So from Chern-Simons formulation, it looks like they are your gauge.
Yes, so this is what I referred to this. So whenever I've written down this three-dimensional metric above here, I said the words which, from a GR perspective, are not completely correct or not defined, locally flat. This means that, indeed, if I translate it now to my gauge field, it's really a flat connection. Yeah, so it's pure gauge.
But does it mean that metric is 0? Because in Chern-Simons form, you can make frame to be equal to 0, right?
We will see, in some sense, what I can achieve. And this is interesting. I can do a gauge transformation. For example, here, in this gauge here, so this A, I could rewrite as a small a, just as J1 DC, and a small a bar as, say, J minus 1, I didn't specify it, or? No, here, okay, J minus 1 DC bar, and probably here minus sign. Okay, I start with this one, which does not have a row direction at all. So if you compute now the metric, then we will see, okay, where do I get the row component from? Okay? But however, what I can do is I can do now a gauge transformation of this form here, namely with B as e to the row J0. Okay? And also with B bar the same. Or the inverse. No, I think it's the same. Okay, I choose B bar and B of this kind, so I'm allowed to do it. And now I compute A tilde and A tilde bar from this connection here. And you will realize A and A tilde bar are precisely this one and this one here. It's a simple exercise. So in other words, it seems I have a gauge degree of freedom, I get a gauge transformation, I can do gauge transformation. Somehow I can get rid of the radial coordinate. It emerges somehow. Okay, this is not precise, they are just words, but this is what you can really make precise on this level, and I can even make it for this three-dimensional metric here. I can this row dependence I can reinsert by using such a gauge transformation.
Are there more questions?
In the last slide, is there a bar missing here? Is that bar?
No, it's definitely a bar missing, but I think the A bar, it's an A bar C. So these are the two A bars, so it's an A bar C, which is also here. So here I've got only a DC bar, but it's not in C. Okay, thanks.
How can you read which scalar curvature?
Sorry?
How can you read scalar curvature?
Here?
Yeah, in your formula.
No, okay, it's not really simple to do it with the gauge field. So usually what one does is we compute the metric and then we compute in the metric-like formulation.
More questions?
Actually, we want to try to formulate gravity with a field line. We can do it another way, which is called the frame-like margin. So what's the advantage of this kind of?
Oh, this is frame-like. So.
But we can do it another way. Rather than using the theorem of the spin connection, we can just do the spin connection and isometry generators.
Yeah.
But rather not decompose into the SR2 and then SR2 plus SR2.
Yeah, so here basically I assumed that E and omega, they are independent. Yeah. So okay, so one hint, because you want to work on higher spin gravity, all of you. What do we have to change now to do like couple and spin 2 and spin 3 degree of freedom? What's your guess? Change just the gauge group from SL2 plus SL2, or gauge algebra from SL2 plus SL2 to SL3 plus SL3, and you couple and spin 2 and spin 3 degree of freedom. Or like do it for SL4, then you couple and spin 2, spin 3, and spin 4 degree of freedom. Do it for SL5, then 2, 3, 4, 5. And then the big question is, oh man, we have this at hand. We know what Chern-Simons A minus Chern-Simons A bar is. Could we basically compute this in the metric-like formulation, and then we would have an action for higher spin gravity. And this was done, but unfortunately only up to the quadratic order. So this was done by Stefan Theisen, Andrea Campiglioni, and Stefan Friedenhagen, and probably his fourth author, Pfenninger. And so they did it. And they told me this is a mess at the quadratic level. We don't see any pattern emerging. The like higher order terms might be even more difficult. But in principle, we have something at hand now. It's just plugging in and calculating. So now you can write on paper. Let's see when we see it on the archive.